All right, so today we are not exactly taking a sidestep journey or anything like that, but we are using weathering and erosion and the ideas we laid down with sediment to go into a related field, I guess, for lack of a better word. And I hope as we go through this, you'll see why geologic time is related to what we've been talking about. There's another, as I told you a few weeks back, there's another conversation about something called stratigraphy. And I've really just been doing the two of these only for the last couple of years, and I'm still going back and forth in my head as to which one, if one should go before the other. And as I'm getting ready to start this morning, I'm like, oh, you should have talked about stratigraphy first. You should have talked about stratigraphy first. But we'll see. We'll see how this goes. Hopefully you guys won't be just blinking at me because you're missing vast swaths of information or anything like that. If there's any concepts that should have maybe been nested into this and aren't, in other words, something that you feel like you're missing some back context for, please ask. Please raise your hands, whatever. So, geologic time, okay? You should have had this. I'm pretty sure you would have had this in Earth Science. Goes anywhere from talking about radiometric dating to, I'm not going to have you memorize the time scale. Don't worry about that. You are familiar with that. To the original way that we did Geo Time, which was not using radioactive decay. It was looking at and staring at and thinking about sedimentary rocks, which is why, as I said, this ties in. These words might mean something to you. There's two ways to look at time. There's relative and there's absolute. All right? And we actually do this in everyday life. You start with absolute, just, okay. She's 19, he's 21, the baby is 3. We're putting numbers. Absolute is numbers, okay? Relative, on the other hand, would be that he is older than she is, but they're both younger than that guy is. All right, it's comparative. Which one do you think we could do first? Yeah, relative. Okay, because the other one, I don't want to say it takes more science, but it certainly takes different science, more advanced science. That's the one that uses the chemistry, going in and looking at the radiation being emitted and so on and so forth. But I don't want to undermine the importance and once they had the ability to do absolute dating, they went back, of course, and looked at all the rocks that they'd worked on for the last 200-ish years, 150 years. And they were right. So it really says a lot for these relative dating principles that we're going to talk about. Just because they're more basic, or some of them I'm going to call them, well, duh moments, okay? They're just common sense, but somebody had to point out that common sense applied, so to speak. Until you see that, it's easy to write these off as just, oh, these are just principles, or it's a lot of thought, and it really worked out nice. So we're going to talk about relative first, and again, I find myself telling you more so what you don't have to worry about than what you do have to worry about for tests. I hope that's almost as helpful. I'm not one of those guys that makes you tie somebody's name to an accomplishment. All right? Hardly ever. This isn't a history class. Okay? And I always hated that too. Which king did this? Which king did that? I don't know. There's 6 kings. They're all named George, and they just have a different number after them. I could never remember that crap. And maybe that follows me into being a teacher. I don't know. But I'm telling you about these guys, and you can't talk about them without using their names. So one of the first folks to think about this stuff was Steno. And Steno, as you can see, 1638, a while ago. He worked in Copenhagen and died 1686. Didn't live too horribly long. They didn't really back then. Some folks did. Steno is one of our founding fathers, except he did it before we really had a field to found. They went back, though, I think, and said, oh, look at this guy's principles. These make sense. So 3 of them that you guys will come to know and love. Principle of superposition, principle of original horizontality, and principle of lateral continuity. So again, I'm not going to say which principles did Steno come up with, but you are going to need to know what each of those 3 is. Or when did he come up with them? It's meaningless. We got 4.5 billion years worth of history. Another guy was Hutton. Good bit later. He came up with something called cross-cutting relationships. This is odd. Why would I define inclusions, but I didn't define any of the others? Sorry, going the wrong way. All right, we're not gonna worry about this one for a moment. So those were some of our founding fathers. It's kind of a weird introduction. I apologize. I think I had a different version of this. That's what I was looking for. Where I arranged this stuff slightly differently. Because we're going to talk about philosophies now that were going on at the time, and why, I guess, to give you a little context, why these guys had to, what spawned them to maybe sit there and stare at these rocks and think about them. Because there were a handful of thoughts out there. I mean, and here's the thing is, we talked about this during the Nature of Science lecture, way back when. Okay, and I always made the point of saying, well, that's the person who first published it or who got credit for it. All right? And I called these folks that came before them sort of early observationalists. I'd like to think that we've been, staring at rocks for way longer than 1637, whatever that date was. All right, well, that's when Steno was born, but you get my point. We've been looking at the world around us and thinking about it forever. You go back to the ancient Greeks, for example, all right? Lots of geology going on there. Da Vinci is another one. He gets credit for a lot of other stuff, all right? But he did a lot of geological thinking much later, don't get me wrong, than the Greeks. But my point is we've been, we came together as a species, sitting in caves and being bored and staring at rocks and telling stories and painting pictures. Okay. So this information that we're giving you, these aren't the first people to think this stuff. I know you guys probably don't think that, but it's important to get it out there. And that's what's almost more troubling when we get to these philosophies. You're like, really? You guys have been paying attention to the world around you for this long, and you came up with Neptunism? So, Neptunism was a school of thought where all rocks grew a very, very, very long time ago in a giant ocean. Worldwide ocean. Now, I always try to give credit where credit is due. I always try to find at least something good in something really, not so good. They are horribly wrong, especially about igneous, and especially, this is going on over in Europe, you have to imagine, right? This is where most of our thought came from at the time. There was all kinds of Eastern thought, don't get me wrong, but we didn't have access to it. And, even still nowadays, they're still very closely guarding the majority of their dinosaurs that are found, like in China and places like that. And that's been going on for a very long time. So, all this stuff is coming out of Europe, and it's all a bunch of old dudes. Very little women in science back then. There was a couple. Paleontology actually had a couple. Because they were the ones walking behind the mule with the guy, and they were picking up the rocks and staring at these cool things that were in there, and the guys were just worried about the rocks. So they were paying attention to the fossils, which was kind of cool. But otherwise, it's same thing you find today, rich white dudes, right? And why? Well, because they could go to school. And they had free time, which is almost more important than going to school. Everyone else was out working all day. They could sit in the study with other people and drink cognac and smoke and discuss things. Free time in school. So you're going to see a lot of rich white guys coming through here. Anyhow, Neptunism. All right. Point being, they grew up around volcanoes, and they still were claiming that igneous rocks came from the ocean. They literally could have just traveled to, Italy and seen these lava flows, not necessarily coming actively down the mountain, but obviously they had flowed down the mountain. But I said I was going to try and find some good in this. So, worldwide ocean. They were thinking big. They were thinking old. Primeval, long time ago. So they did bring in the concept of an expanded time. Okay? Because again, even back then you had the idea that this was a very sort of short-lived Earth. I don't know that they had the number of 6,000 years back then. That's the one that some folks that don't believe in a lot of this stuff still adhere to. All right. But the idea in the West of old Earth was not very prevalent either. So this acknowledged that. This acknowledged the fact that there was a whole lot of water out there, not just what they could see in the Atlantic or the Mediterranean. But otherwise, not so right. Catastrophism. This was an interesting one. These guys, I think, were paying a little more attention. But again, sort of an extremist group. They're saying that the only majority of the only changes were caused by major catastrophes. All right. I don't know that they had the concept of asteroids smashing into the Earth, so to speak, yet. They tied this to the Bible, as you can see here. I don't know. I'm not trying to imply that the 6 catastrophes were the 6 days of creation. I think they just had, as a corollary to it, as a counter to it, okay, they had their 6 major catastrophes, the last of which being the Great Flood. Now, if you want to start a conversation with the geologist about mixing science and religion, the flood is a great place to start. I won't go off on that tangent too much, other than to say that every society has a flood story. All right? And if you follow those flood stories back, they all go to about the same time. And that time period brings you right around to when the ice ages were ending and sea level was rising. So, but like I said, that's a much longer and a much not really this classroom conversation. So, you had a question, sir? Just tying it to current political words. I don't know. I almost said right wing, and I just opted not to use that word. So, but my history's pretty shoddy. You might actually be being ironic, and I don't know it. But what? I can imagine them being well, there's always been doomsday cults. I'm not exactly calling catastrophists a doomsday cult, but you know. You don't think that's extreme? Okay. Okay. All right. Well. Things were different but the same. There you go. A couple times at least. Short memories. All right. Anywho. So, catastrophism. And again, we're going to get to a point where we actually want a couple of their talking points. Okay? Not everything was the result of a catastrophe, but you certainly can't ignore the effects of catastrophes at all. All right, another dude. So Hutton introduced the idea of a cyclic Earth's history. Continents eroded, washed into the sea. That seafloor then is uplifted to form more continents again. That's pretty wild. Again, he's acknowledging a handful of things, possibly putting together in not the exact right order. But again, he's acknowledging weathering and erosion. He's acknowledging that rocks did come from, some rocks came from the ocean. He's acknowledging uplift. You got to understand, at this point, we were also talking about, weird things people believed or what was being put upon them and so on and so forth. We're also coming from a point in time where thoughts about fossils were, maybe the animal crawled in there and got stuck and died. Or when you are a mile high up on a mountain and you find a seashell, well, the ocean must have been that high, which is not a huge jump in logic, right? But they hadn't thought about stuff like uplift. And maybe you guys don't even know what uplift is. Uplift is the idea that when continents or plates can come together and they actually smush up and make mountains, okay? Or there's other ways. They can ride up on one another. But smushing together and making mountains is the easiest way to think about that. And you do get seafloor. All right, the video we watched the other day. Top of Mount Everest. You're finding ammonite fossils, which are nautiluses. You guys know what nautiluses are, right? They're ancient relatives of a nautilus. It's really easy to think that, oh my gosh, the water was this high long time ago. But no, those rocks came together, smooshed together. For those of you at home that can't see me, I'm making a thing with my hands where I'm bringing my two hands together almost like like praying or something. But I'm simulating the mountains going up from two plates. Plutonism we might get to. Unconformities, okay, definitely you're going to have that. Hutton acknowledged the idea that there were gaps in the rock record. Gaps of time. And again, that's huge for right around here. time-wise. Because, again, we didn't have radiometric dating, but we were certainly putting forward the idea of rocks representing time. So, again, even though he wasn't 100% on with this cyclic, there was something here. It drives them nuts. I do the same thing in my Earth Science class when we talk about astronomy, and we go through and talk about, and I hope your teachers did this too, all the guys that were wrong. All right, but then we say, well, they were wrong, but there was this cool idea, and it's that wrongness sometimes that makes somebody else think. All right, like, well, Hutton said this, and yeah, that was kind of right, but what if you did? So it's weird for folks not in science that we pay so much attention to the people that were wrong. But you really can learn a lot from that. You really can. And for all I know, that's prevalent in other fields too. Maybe it's a huge, fundamental tenet in economics or something. I don't know. I've never studied that stuff. But to me, it seems like, and from the looks I get from you guys over the years, why are you telling us about all these guys that were wrong? All right. This is in quotes, so this must have been something Hutton actually said. We find no vestiges of a beginning and no prospect of an end. Again, introducing the idea of what we'll come to call deep time. Okay? He said that weathering and erosion, given enough time, could make the Earth as it appears now. And he relied on the known processes. In other words, you look out the window, what do you see happening? And also, I don't think it says it here, but the rates that it's happening in. And there's going to be a vocabulary word. Those of you that remember Earth Science from 5 years ago will probably remember that word. So the processes and the rates made what we see today, but in order for that to happen, lots of time. Okay? So Hutton was the first one to really just come out and say, hey man, we need a lot more than 6,000 years for this to happen. A lot more. And again, if they had simply crossed over and talked to some of the folks in Asia, a lot of those cultures had huge amounts of time. Of course, they also had us back on the backs of a giant turtle or this, that, or the other thing, but you take bits and pieces of everything. Actually, I think we're on the backs of elephants, but there's elephants on a turtle. That's an author. All right, anyhow. Lyell. Hutton and Lyell, big names. He published in 1830, Principles of Geology. I tried reading that. Oh, good Lord. Horribly dry. Cumulative effects of small daily changes equals the Earth as we know it. And he pushed about what I introduced just at the previous slide. Same rates as we see going on now. And perhaps you see this counter building against the catastrophists. Okay? Everything happens only because of giant catastrophic change. No. Slow and steady wins the race. And of course, with most things, you're going to meet in the middle. I'm going to look, when I get to my office hours today, for another geologic time PowerPoint. If I don't find one, I'm going to rewrite this one. Because I have no idea why I would talk to you about neo-uniformitarianism without talking to you about uniformitarianism. Now, of course, we did talk about uniformitarianism, but we didn't use that word yet. And there's a couple times this has happened already. So I really think that I rewrote this at some point, reorganized it at best, because we're talking about these theories and ideas, but I'm not dropping the vocabulary terms for them. And then in the first couple slides, when I did drop some vocabulary terms for them, I didn't give you any definition slides. And I could have rattled them off. I've been giving these same lectures for effectively 25 years. So they're in my head for the most part, but you guys are, used to seeing the stuff there on the slides. I'm going to work on that, okay? The major ideas will be the same. Nothing's going to change that way, but there should be some more explanatory elements to it. So that uniformitarianism, again, you've heard it before. That's the one that says the present is the key to the past, okay? That's where we look to, and this has been a theme for a couple slides now. We just didn't give you the word, as I was saying. The stuff that's going on out there now, at the same rates, given a lot of time, will give us the landscape that we see, okay? That's uniformitarianism in a nutshell. Uniform. That's what I paraphrased as slow and steady wins the race. Well, neo-uniformitarianism, or we're going to see on the next slide, I think it's sometimes called actualism, what's actually happening. All right. Neo-uniformitarianism addresses, we shouldn't use a negative word there, addresses the rates. Because you know what? Things haven't always been constant. There was a time when we got hit by a hell of a lot more asteroids and meteorites than we currently do. Okay, it was called the period of heavy bombardment. And I talked about that. Look at the moon. See all those craters? We should have just as many, if not more. When's the last time we got hit? When's the last time we got hit by one? A significant one? It's been a very long time, thank goodness. Okay? So there was a period of time when they hit us a lot more. There was a period of time when there was a heck of a lot more volcanoes erupting than currently. And arguably you could say the same for earthquakes. Those are a little harder to find evidence of. So that's where neo-uniformitarianism is going to say, whoa, yeah, you're right, but think about it. There were times where, some things happened more than others. Arguably, there was a period of time maybe where it rained more. There were 6 periods of time where it rained more than it might be right now. There was a period of time when it rained less. Heck, there was a period of time, a rather large period of time, when we were covered by, half the planet was covered by a mile high of ice. And that was cyclic too. So, it's hard to pull out the things that we know and take for granted in our minds. The average non-science student who's basically just been sitting through 12 years of public school or whatever, you'd have to pull so many things out of your head to get where even the learned folks back then were. All right? And it's really hard to do, to think like they thought. We could pretend, they were much more or much less. It's like trying to picture $10 million. All I see is a giant pile of money and maybe Scrooge McDuck going through it here and there. I can't picture $10 million. It's hard to think like they thunk. Thinked. Thunk. Think, thank, thunk. Thank. I guess it would be think. Hard to think like they... Yeah, thought would work. Think, thank, thunk, thought. Throw another conjugation in. It's hard to think that's the most accurate one. It's hard to conjugate like I do as well. So actualism. Actualism is definitely where I am. I don't want to say, you still got all of these folks out there. I hope we don't have any Neptunians out there still. But there's certainly folks who, lean one way or the other. But I really like actualism. I like to say it's what's actually going on. It removes the idea of uniformity from uniformitarianism, which just leaves us with Itarianism. But at any rate, that was a joke. So even though the rates and intensities have changed, the laws of nature really haven't. Okay, gravity still has worked more or less in the same manner. Water's always flowed downhill. Pressure is always moved, from one direction to another, and so on and so forth. That kind of stuff hasn't changed, and as such, the processes should be fairly similar. But we cannot assume that things were constant, and more so, we also need to acknowledge the fact, bring the catastrophists back into the fold here for a moment, that there were some significant events on this planet that certainly changed not just life on them, but oftentimes, the landscape of the earth. Usually when we think of the catastrophes, we do think of the critters and the plants. But, we could certainly talk about some that changed the landscape as well. So, actualism. All right, so the next slide is switching over to absolute time, which is the numbers stuff. And as I said, there was argument for me to do the stratigraphy first. I know these definitions are in the stratigraphy lecture. So I might just leave this one alone in retrospect, even though I said I'm going to go into my office hours and rewrite it. But what I might try to make a promise to myself is in the future, I will definitely do stratigraphy before I do this one. So you'll always have those names and terms and definitions. You already have them in your brains. But you'll see. And we'll be there on Thursday, so it's not that big of a time gap anyhow. All right, so what I tried to construct was an idea of how we thought about the planet before Marie Curie did her thing, okay? And after she did that, you guys know what Marie did? No.
She studied into radiation. I watched an entire video about her laboratory. It was radioactive.
Oh, yeah. Yeah, she basically killed herself with radiation poisoning. So there's a lot, and maybe I ought to show a little. I'm sure there's a YouTube video for 7 minutes on her. I honestly can't remember what her work was supposed to be doing, what she was trying to do, but she ended up, the story that I know, all right, and again, who knows how accurate that is, other than Google and Wikipedia and probably Alexa. What? Well, you're Googling it, yeah. All right. Read me what you Googled.
Discover new elements, understand radioactive decay, and develop medical applications.
What's that, ChatGPT? That's even not enough for them.
No.
Who summarized that? Was that one of those like top of the page summaries? Yeah, garbage. Yeah. All right, so my story is much more interesting, as always. What I remember hearing is that whatever she was studying, she would put her, at the end of the day, she would put her film in the drawer with her specimens. She's cleaning up to go home. And she'd come back the next morning, and the film was always exposed, ruined. And couldn't figure out what the heck was going on. And here it was the radiation being given off by her samples. It was ruining the film. And I also remember that her husband, Pierre, died by getting run down by a donkey cart. All right. Now, again, and how many donkey carts you've seen, but if you've been to Central Park, you may have seen the horse-drawn carriages, and you've certainly seen stuff like that on television or movies. But in my mind, to be able to get run down by a donkey cart, I think you probably had to have been pretty addled by radiation poisoning in the first place already. So, donkey cart aside, I don't think he would have lasted much longer. She's credited, I believe it's radium, that is credited to what she actually discovered. I think they made, there's another one, curium, I think is another element. Don't quote me on that one. But they ended up in a sort of honorary of her. But I think she was studying radium. Now that I will find in my office hours, a little video, and I'll put it up there for you guys to watch. But she basically discovered, for lack of a better word, the idea of radioactive decay. Okay, the idea that certain elements give off energy. I don't know that she quite realized that it was the whole moving down the periodic table thing. We're going to get into that. Okay, I'm not sure again to what level she processed it all, but the idea that this stuff can give off what we would come to call radiation. But yeah, unfortunately, it made her quite sick, and she didn't get to do too much with that knowledge. But yeah, Marie Curie, very important scientist, not just lady in science. But let's talk about the dudes instead. Lord Kelvin. I made it a scary long way before I found out that wasn't his last name. It's not like he was Bob Kelvin or anything like that. It was a title, Lord of Kelvin, something like that. Now I got to put his name in parentheses here at any rate. But if you know Kelvin, he did a lot of neat stuff. We got minus 273 Celsius to thank for him for that one, absolute zero. But he used that knowledge to think about the Earth. And he knew cooling rates, or he thought he knew cooling rates. He knew cooling rates more than the average person knew cooling rates at any rate. And he started with the idea that at some point the Earth was molten and it cooled. All right, that's pretty important. I wouldn't say exactly groundbreaking in 1890. I mean, that's barely over 100 years ago, right? At least when I started giving this lecture. Now we're looking at, 135 years ago or so, 130 years ago. So he figured out the size of the Earth, Googled it, like you guys do. He had the melting temperatures of a handful of rocks that he knew about, the cooling rates, and he came up with a hugely varying number from 20 million to 400 million years old. All right. But again, it's not necessarily about that, but that he put some really neat ideas together. Okay. First of all, he blew way past that 6,000 years, and he arguably had data, in air quotes there, to support it. Okay. He says, look, we can't, and this is what Lyell and Hutton were doing. We can't have what we see in this short a time period. Okay. But all they had were their thoughts. Look at that cliff. That can't have been made and built up and then, the river cut back down through it in 6,000 years. Can't have happened. Well, if you do, okay, fine. You can't argue with some people. But Kelvin came in and actually says, okay, we know that rocks take this long to cool. We know that we could argue that even though we don't see igneous rocks all the way at the surface, but arguably there was a point in time when all of this was one big molten mess, and so on and so forth. So he had some data. He didn't, however, know about the fact that the Earth, the interior of the Earth, is continually getting new heat added to it because of radioactive decay. All right. It wasn't just like you heated up some iron in a forge and set it down on the counter and waited for it to cool. How long would it take to cool? That's sort of the way he approached it. Now imagine that same ball of iron trying to cool if there was a low but background and constant source of heat inside of it. It's going to take a lot longer to cool. So again, he was wrong, but he was definitely going down the right track. Definitely. And introduced some really great ideas. So the Curies, 1903, not that much longer, realized that radioactive decay produces energy, heat, and literally there it is, 2 years later, all right, we were putting that together to realize that we could use it to date rocks. Now we're going to talk about those processes that they used, and you're going to think that perhaps it's not that intuitive. Yeah, to the right person it was. To the folks that had spent the last however many decades of their lives studying chemistry, brand new chemistry, alchemy morphed into chemistry, so to speak. But, the relatively brand new field of chemistry, they were able to put these pieces together and come up with a really neat idea. So what's the idea behind radioactive decay? The idea is that some atomic nuclei are unstable, all right, certain elements, and they will transform into a nucleus of another element, or I should say this here, but I don't, another version of the same element along the way. Uranium is one that comes to mind. There's uranium-236. I'm going to make up a number, uranium-235. Okay? There's a bunch of uraniums. Remember that number that you see with these things is its mass. Okay, it's going way back conversationally, but there's a reason we introduced that idea. You have the atomic number, which is the number of protons, which would tell you that this is uranium. But then underneath that, the smaller number on the bottom of that little square was the mass. And that's when you hear carbon-14 or carbon-12 or uranium-236 or strontium, and I can't remember what the number on strontium is. Strontium goes to rubidium, I think, is another decay series we talk about. Those are all different, and the word we used back then was isotopes, right? Different versions of the same element. Anyhow, what they found is that they could actually measure the rate of decay. They could say, okay, it takes this long to turn from U-236 to U-235. And then they go into these rocks and they measure the amounts, ratio-wise, okay, of the two uraniums. Or let's just say we've already gone through the whole thing and we're looking at uranium, which decays to lead, is what they say, okay? So we're going to look at the total amount of uranium, total amount of lead, do some relatively simple math once you measure all that stuff. Do a little math and say, okay, this has been decaying for X number of years. Therefore, this rock is that old. A lot of folks didn't believe that for a very long time, primarily because it gave them numbers they didn't want to see. Like, that's too old, that can't be right. We still have people saying that nowadays. This process has gotten a lot more refined over the years. It's literally to the point where, if there was a reason to, there could be a vending machine in the lobby of Walmart. You put your rock in, give it $5, and it would tell you how old it is. It's not hard, okay? Again, especially with the technology we have today. Last I remember, and this is going back, I can't remember the last time I got a journal from like Geological Society or something like that. There was a little ad in the back that you could mail them your rock and $25 and you'd get a date back. Okay, that was the 90s. So like I said, we're totally, if Apple decided to put sensors for such things in there, there would be an app for it. It's not hard. That's just sort of a geologist's dream, but, it's not hard to do. So it is a science, and please, there's a lot of things to argue about in this world, but radiometric dating, radioactive decay isn't one of them. Now, there are aspects of that certainly you could pick at, but they're much bigger than just the data coming back from the labs. So you guys remember these: half-life, parent, daughter, good times, right? So half-life is the amount of time it takes for half of the parent element to decay into the daughter element. And I still have people getting these questions wrong on there. Parent, you know how the birthing process works, right? Parent is what you start with. Daughter is what you get, okay? Now, I don't know why they said parent and daughter instead of parent and son. It doesn't matter. But I've had people pick, and this is, I'm just thinking of one of the multiple choice questions, daughter makes parent. When does that ever happen? Please don't pick that answer. Okay, anyhow. The neat thing about half-life is that arguably you never run out. At some point you will get too small to measure accurately. But, so let's just say as an example, right now I'm going to walk halfway to the door. All right? We'll call it this line right here. So that's one half-life. Now, half-life for each element could be different. It could be 1,000 years for one. It could be a million years for another one. And don't ask me how they decided that the ones were a million years. You can't obviously sit there and watch that. They have ways of scaling up. So, at any rate, so I've just done one half-life. I walked halfway to the door. Now I'm going to walk another half-life. Now we're at 2 half-lives. I'm halfway to the door. I'm going to go halfway to the door again. 3 half-lives. Halfway again. 4 half-lives. But my point being, it's getting very complicated now for me to say, okay, I've actually done half. All right? Let's say that's half. And what's half of the next one? Same thing is true when you're looking at the atoms, the elements in these rocks. The basic idea behind it is, if you think you have a really, really old rock, you're going to want to pick a decay series that has a big half-life on it, because you want to make sure you have enough to measure accurately. It also makes sense then, if you have what you think is a fairly young rock, that you're not going to want to pick something that has, a 100 million year half-life on it. You're not going to be measuring anything really. I kind of equate it to screwdrivers and jobs you have to fix. So let's say you got 2 jobs today. You have to fix the barn door and you have to fix your eyeglasses. You going to use the same screwdriver for both jobs? No, I hope not. All right, I'd try to use my pocket knife. I'm very, very lazy. Well, I can fix it with my pocket knife. I'll be good. But you get my point, okay? Barn door is going to need a big screwdriver. Presumably it's got big old screws on it. Your eyeglasses, you wouldn't even be able to fit that screwdriver in there. It's the same idea. You pick the right tool for the job. And again, that goes a long way towards, when people start arguing about this stuff, yeah, they've thought of that, okay? They accommodate for the idea that you need the right tool for the right job. All right, so anyhow, the geometric rate versus linear is kind of confusing for some folks. I always used to say logarithmic, and most of you didn't smile and nod at that one. You played with semi-log or log paper in math class probably, and you know that each jump isn't the same, right? And that's sort of what's going on here. And that's because the halves aren't always the same size, right? When I think about me walking to the door, the first half was really, really big. Those last halves, really, really tiny. So here's that table of elements. You may remember it. You may not. What's essentially happening when we call this decay is breaking down, right? So the idea is that you pick, I don't say any element because, we use a handful, but you pick an element and you move down an element or two. That one turns into that one. In order to do that, what makes these elements? You guys remember what was the atomic number at the top of it? That was the count of what's protons, right? So if you're going to lose protons, we could arguably just say that's certainly losing some energy, okay? It's losing some protons, but it's mass, matter, energy, it's all the same sort of at that level. So you got to eject some energy. And that's fine. We understand that. Except there's one radioactive decay series where you actually go up. And I get it, but I'm like, really? That's decay even though you're going up the scale? Okay. You'll see how it happens. It's kind of neat, actually. So we pick a handful. I mentioned strontium and rubidium, Rb and Sr. There we go. So it's strontium to rubidium, 38 to 37. Uranium to lead, used down here, it's 92. Lead is Pb. It's all the way back there at 82. There's another one, and it just jumped out of my head. But those are two big ones. Carbon-14, carbon dating, is not the same process. All right? Most of you are familiar with that one. Again, you spend any time watching the Nature Channel. That's a big one because anything from mummies to Vikings to all that cool archaeology stuff. Not paleontology or geology, but the archaeology. They use that. It's a lot better tool for a short job, time period job like that is. And I have a slide about that a little later, so you'll see what's really going on there. But that one's a little different. All right, so we're going to learn 3 types of radioactive decay. Alpha decay, beta decay, and electron capture decay. And when I first wrote this, I'm like, oh my God, these guys, I'm going to get all kind of wrong questions on this. You guys always ace these questions. Like I said, you'll do something really silly like tell me the daughter gives the mother, but you'll get these decay ones right. Maybe you worry more about these so you study them more. I don't know. All right, so alpha decay, what happens? In alpha decay, you've got 2 protons and 2 neutrons are ejected from the nucleus, which means you're losing 2 atomic numbers and 4 mass units. So, again, remind me, why are you losing 2 atomic numbers? 2 protons. Why 4 AMUs? Okay. So both the neutrons and the protons have mass. All right. So let's just make something up real quick. Let me go back a couple slides. Let's pick osmodium here. I think that's what OS is. But I don't know what W is. Hell's bells. All right, let's do zinc to nickel. Again, we're just making crap up right now. All right. So Zn is going to do an alpha decay. Zn, this doesn't have masses on it. I don't want to make up yet another thing, but you get the idea, okay? So let's say that zinc is 100. I don't know what it is. Let's say it has a mass of 100. 2 protons brings it down to nickel, which is 28. All right? But it brings it down to nickel, what did we just say? 96 then. All right? Whatever nickel is supposed to be, it isn't that necessarily. It's going to be some new isotope of it. So way back when we introduced isotopes to you, but we didn't really tell you how we got them. We just assume Mother Nature made them, and she does. But so you were going to say something? I apologize. Mr. Carp?
I've got something to do now.
Okay. What? Since we paused.
The higher the number, the more unstable it becomes.
I don't know that. You may be very right, but I don't know that. When I was in your guys' shoes, I did absolutely miserable in chemistry. I was awesome in lab, but the lecture, I understand way more of it now since I've been on this side of the desk than I did then. In the end, I just didn't study it. I'll be honest. I'm sure I'd like to think if I tried, I would have done much better. But yeah, chemistry and I were not friends back in college. But I'm not familiar with that idea that the higher it is, the more unstable it is. I can tell you, anecdotally perhaps, but maybe to your point, that some of the ones at the end of the table took us for a very long time to find because they are, only detectable for a 1/16 of a second in a vacuum and so on and so forth. But as a straight up progression, I don't know that that's true. Like I said, you may very well be right, but I'm not familiar with that. But californium and I'm not even seeing them, Einsteinium and some of those guys.
I'm just wondering why we need to know the ones that are super, super tiny, like 16 of a second in a vacuum.
I think it's just more of a conquest thing. And this is that and again, this is where my knowledge of chemistry bites me in the bum. This was all predicted, as I understand it. So some guy way back when, Bob Periodic, let's just say, said, you know what, there's method to this madness. I use the Lego thing. You keep adding one little Lego brick at a time. He predicted where there should be elements and what they should be composed of. And it's sort of been a quest over the years for folks to find them. And they filled in a lot of holes. I don't know what his looked like. And again, that'd be a cool little project for me. I've got so many cool little projects, though. But, to see what the first periodic table looked like, how much he came up with and how it changed over the years. But I do know that a lot of it is predictable. And I'm starting to wonder how old this one is that I'm giving you guys.
They came out with new ones recently.
Yeah, and I'm looking at 110, 111, 112, 113. Those should be named by now, maybe. But that's sort of the point. There is, even if we have, arguably they could have found 111 and skipped 110. But yeah, so they know there should be 113. It's just a matter of isolating it, finding it. I've always wondered why they pulled the lanthanide and the actinide series out numerically. Again, the chemistry folks will tell you. Would I have any chemistry fans in here? Why'd they pull them out?
No, I was about to say, what I brought up was not for this. I'm accidentally bringing in knowledge of nuclear reactors.
Yeah, accidental knowledge of nuclear reactors. Okay. What is that? What is the number and stability?
The number is for anything that is nuclear related. So, for instance, bismuth, thorium, uranium, plutonium. The higher the number is, the more.
The higher the higher the isotope of bismuth, the more unstable it is.
Yes.
I could get on board with that.
Increases with the time number.
Okay.
However, like bismuth 83, thorium 232, uranium 238, for some reason they're more stable than others.
I would say that's because it's more of a. Remember when I talked about the happy little atom having equal numbers of protons and neutrons? That should give it the most stability, or at least the closest to equals should be more stable. But you like bismuth? Is that what you said?
I like
Where'd you meet it? Where'd you meet bismuth at? You're just like saying bismuth. Okay.
I ended up doing an entire project on it.
Okay.
Let's choose one element.
Did you ever see a hunk of it like in real life?
I want one, but
Okay.
I have seen them, but wait to get one.
Okay. I don't know if it's radioactive or not. I don't know.
I don't think so. So they're gonna let us hold it.
I was just going to say, I want to say that she's not Professor Geary anymore. She's Professor Williams. I still call her Geary, even though she's been married 10 years. That she had a hunk of bismuth. She texted a picture. I'm like, oh my God, where are you at? I want to come see it. This is a really cool looking metal, if I remember correctly.
QB and rainbow.
But QB and spiky at the same time. I remember the pieces she had these cool little spikes on it. Yeah, I don't. If it is, it's probably hopefully not too horribly radioactive. But I have a Geiger counter, by the way, if you guys ever want to test anything.
I love that.
It's really cool. It's like straight out of 1983, and it could have very easily been out of 1963. But it's that industrial sort of mint green that everything was back then, and made out of metal and very clunky. But I think it works. The company that made it still exists. I called them about calibrating it. He's like, all honesty, if you hadn't used it that much, and I think the last time it was checked was sometime in the early 90s, he's like, it's probably still fine. I'm like, okay. He says, but if you really want me to come out, it's good. All right, so alpha decay, back to the point. Sorry, that was a huge tangent even for us. What time's class done? 25. All right, we got a few more minutes. 2 protons, 2 neutrons. I almost said a different word than he meant. 2 atomic numbers is 4 and 4 masses. Here's a better way to look at it. Maybe not. Yeah. But 2 protons and 2 neutrons, not just 4 of anything. Because if you kick out 4 neutrons, you're going to stay the same element. That's where they get you. Mm-hmm. Yeah, that's what you got to watch. And that's what the test questions are on, too.
I'm scared of this.
Like I said, I always worry about these, and you guys actually always kick butt on these little series of questions. Again, I think because maybe you're worried about it. So beta decay. Beta decay, you're losing an electron. This is actually what blew my mind when I first wrote this, and I actually checked with one of my chemistry pals because I didn't know this was a thing even. A neutron shot off an electron and turned into a proton. Dig that. Okay? So what that does is increase, I told you there was an example here, increases the atomic number by 1. So beta decay is actually going up the chart. Alpha, you're going down the chart, 2 jumps. Beta, you go up 1. Again, by changing one of those neutrons into a proton. And it should not, yeah, it's right here, I'm saying that should not change the mass. So you end up probably with a low mass next element up. Again, created an isotope. But yeah, I didn't know you could just plug electrons in and out of things and change protons and neutrons. I thought they fundamentally were what they were. So boom, a beta particle is just an electron then. Now, why they don't call this electron ejection or electron losing, I don't know, because guess what they call the next one? Electron capture. So in electron capture, a proton is gaining an electron, which guess what? Turns it into a neutron. So you lose an atomic number, but again, the mass stays the same. So that would leave you with a heavy 1 notch down. Again, the assumption being that your mass is always going to be twice your atomic number. As you're seeing, that's definitely not the case. But on day 1, we didn't want to give you a whole bunch of exceptions, right? And so that's what I mean when I say heavy and light. It's based off of the mass should be double, the atomic number. So again, you got alpha decay. You're losing 2, what do we lose? 2 protons to go down. You lose 2 protons to 2 neutrons. That's what I was just saying. I didn't want to say it without checking though. 2 protons and 2 neutrons. That's the only way you could lose 4 AMUs. So you lose 2 notches, jump twice in the periodic table, and you lose 4 mass units. Beta, you're actually going up 1, keeping the mass the same. Electron capture, you're going down 1, keeping the mass the same. And the way we're doing that is either by losing losing an electron from a neutron, or gaining an electron into your proton. Now again, I'm not ashamed to say I don't know, but I feel bad I'm saying all these I don't knows. If this stuff is coming from the shell, remember the electron shell where you've got all your electrons out there in those nice little organization that they made you memorize, 1s2, 2s2, 2p6, da-da-da-da-da-da. I don't know if that electron's coming from there or if it's actually being emitted from another source. Because that's going to change when you want to go balance your equations. Again, not to go any deeper into chemistry, but that should change. If you're stealing an electron from your shell, that's going to change all of the balancing math you've got to do and who could bond with what and so on and so forth. So it gets pretty wild. Huh? Maybe that's why they're so unstable. It could be. That could definitely be. You've weakened the wall, so to speak. But don't worry, there's no philosophical questions about this on the test. And I'm sure the chemists would argue that it's not philosophy at all, but we're simply pondering it. But it's more just the straight up definitions, okay? And the outcomes. So sometimes you've got a single decay step. It's one and done, okay? And then sometimes it's multiple. The uranium to lead is a huge series. And I'm going to show you that one in a minute. But sometimes it's simple. Remember we talked about strontium and rubidium, and they were right next to one another. Potassium argon. I knew. I was trying to remember the other one earlier, remember? Potassium to argon. It's another one. It's just a single jump. But dig this one. So here's uranium to lead. Now, arguably, at this point, you should be able to tell me if this were in black and white and you couldn't see what color the arrows were. You should be able to tell me by looking from, the bottom's cut off here, but by looking at the element that you start with and the element that you end up with, you should be able to tell us if it's an alpha decay, a beta decay, or an electron capture. There's no electron capture in this series. But by doing a little bit of math, right, you should be able to say which way it's going. So we're starting with uranium. We're going to thorium-234. All right, so we're going down a periodic. We're going down 2 atomic numbers. So more than likely that is an alpha decay, right? And we're losing 4 mass units we know in an alpha decay, so we could assume, even though we can't see it on here, that that was U-238. So in one alpha decay, we go from U-238 to thorium-234. We then, thorium, for whatever reason, goes, and there's the other thing. Why do these things choose to do alphas or betas? I have no clue. U-234 up to palladium, PA? I think it's palladium. I want to say it's PL, though. She would know. Professor Barley. No, gone. I think it's palladium. Palladium-234. Then it actually goes back up to uranium again, but this time it's 234, not 238. Then we're back to thorium. I'm not going to read this whole thing to you, but you get this huge series. And when does it end? It ends when you get something that's stable, which happens in this case to be lead-206. So, protactinium. I enjoy saying that one. Protactinium. You said you liked thorium earlier? Just because of Thor, or what?
No.
Oh.
Because of thorium.
All right.
Not having to react.
Oh, okay. Everyone has that stage, you know.
Yeah. Everybody likes to get into fission reactions.
My son does, so I know where you're coming from. He's actually pining for fusion reactions, but we'll see. All right, so how the hell does this relate to rocks? Because we got to get out of here in a couple minutes, literally. So, dating rocks. Extrusive igneous, those are great. Why? Because they cool really fast. What you want is something that becomes a closed system as quickly as possible. Okay? And a closed system is a rock that nothing's going into, and radiation aside, nothing's going out of. It's fixed. Intrusive igneous rocks. What's the problem? Well, sometimes these things can be so big that literally there's thousands of years between when the top cools and the bottom cools, or the outside cools and the inside cools, okay? So you could get actually a couple different dates from it. You go to a lava flow, you're getting one date. Now, you go above it, you go below it, you're going to get other dates because, arguably they could be that different. Again, how fine of a tool are you using? Are you going to see decades show up? Well, if you use the right tool. Sedimentary rocks, really bad idea. Why? Because they're made up of pieces, parts of, you get a fist-sized rock in your hand, you could have 300 or 3,000 different rocks represented in that rock. So you take a piece from here, you take a piece from here, take a piece from here, you could get 5 out of 5 different dates. So this is why, in the end, we end up using a mix of relative and absolute. Metamorphic rocks, more often than not, you're going to get the time of metamorphism, not the time the rock was made. Could still be useful, depending on your goal, all right, but not usually what you're trying to get. This is the big arguing point when a lot of people want to argue about radiometric dating is how vague it is. And what we try to put back is it's relative, and that really says a lot. It goes back to the whole silly argument that I always make of that if you're the average college student or average college professor, you got maybe $3 or $4 in your pocket. If you lose 2 of those dollars, you're going to really notice it, okay? But let's say you are Tim Apple or Steve Jobs or somebody like that, and you've got $1 million in your pocket, okay? If I say Steve Jobs, he's dead, but Elon Musk, somebody else, okay? The Facebook guy. I forget what his name is. Yeah, Mark Facebook, okay. So, you've got $1 million in your pocket. You're not going to be concerned with $2. So it's a relative kind of thing. The older we go back in time, the bigger sort of fudge factor you're going to see. It's just the nature of the beast. But even those aren't huge. They're less than 0.5% typically. Okay, and in some cases, we're looking at 0.1, not even 0.5. So, for example, you've got a rock that's 540 million years old, and you're going to get a range from 540,000 years to, 2,700,000. That's huge for us. But again, the rock you're looking at is 540 million years old. So you could say, what's 2 million years and 540? It's not a whole hell of a lot. And especially getting down to 540,000 years. Again, that's the thing. For humans, 540,000 of anything is a lot. Okay? But that's because we're not used to working typically in millions, let alone billions. Remember, with the Earth, you got 4.5 billion years to work with. So, at any rate. Yeah, we're going to have to finish this up on another. I don't want to just blow this off. All right, so there'll be a part 2.